class we were doing secant, cosecant, tangent, and cotangent function.
Okay.
Find what our right here.
Do you know the graphs of each of those?
The tangent one is it's a periodic thing where it'll cross at 0, 0, and it kind of does that wave in the middle there.
All four of those functions you talked about have vertical asymptotes.
Yeah.
Whereas sine and cosine do not. Okay, tangent goes from minus pi over 2 to 2. Notice that that's the fourth quadrant to the first quadrant. It's always increasing like that. Cotangent goes from 0 to pi. In other words, it also has a period of pi, not pi over 2, and it always is decreasing. It's supposed to go through 0 there. So the blue is cotangent curve. The red is tangent curve. And that's important because a lot of times they'll give you a curve and they'll say, is this a cotangent curve or is it a negative tangent curve? In other words, if we look at the tangent curve, the red one, what would negative tangent look like? Well, negative tangent's going to look like this. It's going to be reflected over the x-axis, and it's going to have exactly the same shape and appearance as a positive cotangent curve. So if I just give you a curve without anything attached to it, and I say it looks like that, without a grid, you don't know whether that is a negative tangent curve or a positive cotangent curve. Could be either one, depending on how I label the x-axis. Okay. Secants and cosecants. The way I tend to think about those graphs is in relationship to their reciprocals. In other words, if I start with the sine curve, I know that the cosecant curve sits on top of the peaks and the bottom of the valleys. I didn't draw this very good, but and wherever sine is equal to 0, well, that creates a problem for cosecant because you're dividing by 0, which means you're going to have vertical asymptotes. So wherever sine is 0, you have vertical asymptotes. You cannot divide by 0. Okay? So if I erase the sine curve, I'm left with the cosecant curve. Notice something else about cosecant. It is never within between the range of -1 to 1. It's always greater than 1 or less than -1. Opposite of sine and cosine. Sine and cosine are always in this range here. Secant and cosecant are always above and below that range. So those are some basics. What specific problems do you have?
So this one just wants us to graph two periods of the function.
Okay.
On a calculator. Yeah, so this one negative cotangent 3x.
All right. What's B?
3.
What's the period based on that?
Would it still be 2 pi over b?
No. With tangent and cotangent, their periods are pi. They're not 2 pi.
Oh, so it's just pi over 3 then?
Uh-huh. Okay, now let's go to graph it. We know that the first asymptote goes there on the y-axis because tangent is 0 there. So cotangent's going to have an asymptote. Where's the second asymptote go?
At pi over 3.
And the next one, because they want 2 periods of this thing?
Yeah, I think we're probably doing, like, both sides of the graph. I think that's what he wanted.
Okay, well, that would be 2 pi over 3. This would be minus pi over 3.
Yeah.
And we're going to have vertical asymptotes right there. Every pi over 3, the new period for this function. Okay, so the only thing we have to do is to reflect it. We got our period down, so what's this going to look like? What's it going to resemble?
So it's just gonna kind of...
It's going to look like the tangent curve. In other words, it's going to start at negative infinity.
Oh, yeah, because that's negative.
It's always increasing because of the negative sign. It would have been always decreasing. This point right here is pi over 6, the halfway point between 0 and pi over 3. And then we draw a negative, another vertical asymptote on the other side of the y-axis. Obviously, it does the same thing. And in fact, it does that. There's 3 periods of it.
Okay.
Okay? So, if I gave you this curve without telling you what it was, your first reaction would be, that looks like a tangent curve, right?
Yeah.
So it's not easy to distinguish between a tangent curve and a negative cotangent, or vice versa, a cotangent and a negative tangent. The only thing that distinguishes it, and perhaps this is worth remembering, the tangent curve straddles the y-axis. By that, I mean it does this. The cotangent curve sits next to the y-axis. The cotangent curve does this. Same with secants and cosecants. And it is worth memorizing that. And that way you can do it without relating it to the original one. Notice that cosecant, the reciprocal of sine, straddles the y-axis. That's cosecant. Why? Because cosecant sits on the tops and bottoms of the sine curve. Okay? Secant, like tangent, straddles the y-axis. Secant looks like this. Instead of sitting next to the y-axis, it straddles it. Why is that? Because it's the reciprocal of cosine, which looks like that.
Okay.
So secant and tangent straddle, and you know what I mean by straddle. It's equidistant on both sides. It's symmetric with the y-axis. Whereas the other two sit next to the y-axis. So if I give you a curve and it looks like this, I know that that is secant, not cosecant. Cosecant would look like this. All right. So specifically, what's your next problem?
Next one is y equals cosecant 2x.
Okay, this is pretty easy. B is 2. What's the period?
Pi over 2.
Cosecants, what's the natural period of cosecant?
Oh, will that be 2 pi then?
Uh-huh. Everything's 2 pi except tangent and cotangent.
Okay.
Both of those are pi. All the other 4 are 2 pi. So this would be 2 pi divided by 2, or pi.
Okay.
Cosecant sits on top of the sine curve, so it sits next to the y-axis, not straddling it. In other words, it's going to be here. Let's draw our asymptotes. In other words, one asymptote goes through there, the other asymptote goes through there. What's this point right here?
I think my teacher called it the average.
Well, there's 2 asymptotes to draw an entire period of the cosecant. In other words, if I put the sine in there, I have to go to here to get one full period of it. Okay? So the cosecant is going to sit on the peaks and valleys of the sine, and in case you don't remember why that is, if sine is equal to 1, well, the reciprocal of 1 is 1. If sine is equal to -1, the reciprocal of that is -1. So these always have to meet right there at 1 and right there at -1. And again, you don't have cosecant if sine is 0, because you would be dividing by 0. So I know that typically this would be 2 pi, but since this has a period of pi, I'm going to label that pi right there, not 2 pi. Let's take out the sine curve, and there you have it. There is one period of cosecant 2x. This is obviously pi over 2 right there. But the period of this, don't make the mistake of thinking the period is the distance between the vertical asymptotes. It's the distance between 2 vertical asymptotes. What else?
3 tangent x over 2.
What's A?
3.
What's B?
1/2.
And what's the period?
So would that be 2 pi?
Where's this asymptote go? And where's that asymptote go? In other words, label the x-axis for me here.
Okay. So that one on the left would be at -2 pi?
No. For tangent, the distance between the asymptotes equals the period.
Okay.
In other words, I can draw one full period of tangent with two asymptotes. Typically, the tangent goes from minus pi over 2 to pi over 2, which is a period of pi. So if I'm going to double my period, then I'm going to have to go from minus pi to plus pi. In other words, I'm expanding it horizontally by a factor of 2 when I do this. And in case you ever have any doubts as to your graph, whether it's right or not, in other words, should I have gone from 0 to 2 pi instead of from minus pi to pi, if you're asking yourself that question? Well, notice that when I plug in 0 for x, tangent of 0 is 0. So I still have to go through that point right there. Okay, and if I plug in pi over 2 for x, it becomes pi over 4. I know that pi over 4 is equal to 1, so I know that point is on my curve also. And it has to be at pi over 2. So I now have no doubts whatsoever that this is the correct curve. It fulfills my basic points. In other words, I know the tangent of 0 is 0, and I know the tangent of 45 degrees is 1.
So how does A affect the graph? Does it do anything?
Yes, sorry, I didn't take that into account here. Good point. I made a mistake. It does. Instead of this point being 1, it's 3.
Oh, okay.
Sorry. In other words, without the 3, tangent of pi over 2 would be equal to 1. In other words, that part would be equal to 1. Well, if we multiply that by 3, we get 3. So it does act as a vertical stretch. In other words, let's take that 3 out of there. Let's make it the typical 1. Let's put 3 up here. Okay, well, the net effect of that 3 is a vertical stretch factor. So instead of being the shape that I drew, it's going to be more like this. Notice that at pi over 2, it's now equal to 3.
Okay.
A vertical stretch for the tangent curve is like if this was a piece of string or wire, and you pulled up on that end and down on that end, you would create a vertical stretch factor.
All right.
Yeah, thank you. I take that into account when I first drew it. But the only way you can really tell that it has a vertical stretch factor of 3, it's not real easy to tell from looking at the curve. I mean, all the curves kind of look like this, right? So is that vertically stretched? Yes. So the only way to tell is to have this marker over here at 3. And then you can tell that it's been vertically stretched. Okay, what else?
3 secant 4x.
So A is 3, B is 4, what's the period?
Pi over 4.
Period is 2 pi over B.
Oh, right. Okay. So 2 pi over 4, pi over 2.
Okay. secant, being the reciprocal of cosine, would typically look like that. That would be one period. In other words, the very first one's going to straddle the y-axis. It's going to sit next to the y-axis. It's not going to straddle the y-axis. Okay? So the only difference between this is what is this point and this point.
Making it 6?
No, 3 and minus 3. Because typically those would be 1 and minus 1, right?
Yeah.
Okay, so it's 3 times that.
Okay.
Okay? In other words, that 3 is just like any other leading 3. It's going to vertically stretch. It's as if somebody tugged up on the top one and tugged down on the bottom one. Now the only thing left is to put the period on it. What's that right there? In other words, from beginning to end is how far?
That's pi over 2.
Okay, so we'll just label that pi over 2. And the only other key point is that middle vertical asymptote, which is at pi over 4. Of course, you have another one right there. And you have one on the y-axis. And so we've been vertically stretched and we've been horizontally compressed. Because normally, without the 4 there, if I just were plotting secant of x, then this would be 2 pi and this would be pi. So we've been horizontally compressed by a factor of 4.
Okay.
What else? Yeah.
Looks like that's about it.
Okay. Let me draw a graph and see if you can come up with the function.
Okay.
Let me label it. No, let me label it different. See, that would be pi. So it would be 3 pi over 2. Okay, that's enough to label it. So, in order to figure out what this sinusoid function is, let's look at A.
So that's 2?
Yeah, because normally at this point here, tangent would be 1, or cotangent. Okay, what's the period of this function?
2 pi.
Which makes B what?
1/2.
Which makes our, are we looking at tangent or negative cotangent?
Negative cotangent.
So what's the final formula?
Negative 2 cotangent of 1/2 x. X over 2.
There you go.
Alright.
I don't know what else to tell you about graphing these. I think that covers it.
Yeah.
All right. Any last questions, Daniel?
No, I think I got a pretty good handle on this
Yeah,
now.
I think you do too. Sounds good. I will talk to you, let's see, Monday or Tuesday. When's your standard? Monday evening?
Tuesday.
Tuesday evening? I'll talk to you Tuesday. I think at 7, right? All right. Bye-bye.
Bye.